Hello there, welcome back. My name is Al and you are watching Al's C++ tutorial series, which has yet to actually touch on the topic of C++ in any serious way. However, I believe that at this point we've made some progress in learning about what's involved in actually creating a computer program. Actually almost from scratch in our case. And I'd like to review where we are now and where we're going to go to after this point. Now, we've looked at making simple COM programs. We looked at the segmented architecture of the 8086 processor. We looked even further behind that and have at least gained a little bit of understanding of what would be maybe not required but desirable in a computer programming language. Now, if we could take what we already have and add in some of those features. But I think the next logical step, to save time anyway, would be to move to a semi-structured programming language, C, at this point. And since you're already familiar with C, that shouldn't be a difficult step. So we'll see how what we've learned will help us understand how C works. And then we can move on to C++ finally, hopefully within the next couple of lessons. I'd like to just also take a quick look back at our segmented architecture here. I was looking at this table here that I made before with the segments broken up into 64K chunks. Now, this is just really going back to a previous lesson and the one before it, several ones before it. However, it might be of some interest to you. It's possible to get a printout of the memory usage in our little world that we have. We've seen some of this, the interrupt table at position 0. 100 possible interrupts, 4 bytes each, makes 400 bytes worth of interrupt table. And here are some communication areas, probably for data transfer. Here are some of those standard devices that I mentioned before, 5 of which are included in your JFT, the job file table, if you recall. Mem here is the program that was running to create this output, so it's in the list. And then there's this graphics bit I thought you might find interesting. Turns out that in text mode, unavailable to someone running Windows 7 like me, text graphics memory starts, in fact, well, in the B segment. If you're thinking of it in terms of this, in terms of this picture, 0, 1, 2, 3, all the way up to A, which is the beginning of video memory. B is the next segment, and that's where graphics memory is held. Let me show you by example. If I make a lot of printout here, and go into the debugger and dump B800 is for color graphics. you'll notice that this printout is related to what's actually written here. 7/22/2013, 07, and so on. The second byte is an attribute byte. The first is a character, the second is an attribute, and the attribute for this particular character goes by foreground and background. So background and foreground. Foreground here, in this case, being white. The way it works is like this. It's 4 bits for background, call them B's, and then 4 bits for foreground, like that. Now, the highest bit in both cases means bright or not bright. So in our case, this is all zeros. So the background is black, and the foreground is 7. And these go, I believe, red, green, blue, but it could be blue, green, red, and we can test that in a minute. This is not bright color, and equal amounts of red, green, and blue, however the order is. Pretty certain that green is the middle one. Now, how can we test that? Well, we can go into the deep first. Let's try and figure out the position of one of these columns here. This happens to be 50 rows, 25 and 25. 25 rows is called a page, it turns out. And we have 2 bytes per character, and this is 80. The width of this is 80 characters. So if we wanted to go to the 20th row, the 20th row would be 20 times 80 times 2. That would be the offset of the 0th character in the 20th row. Now, I would like that in hexadecimal. That would be C80. So now, if we go to position C80, the first thing will be a character, and the second thing will be an attribute. So let's try entering D800, offset C81, let's say, because we want the attribute. I'd like a 0 for the background still. And if we want to just pull out the top of the bits, remember it's going to be 1111, and so just 3 1s, 0, let's say 100. I'd like to determine whether that's red, green, or blue. So that would be 1, 2, 4. So that'd be 4. So let's see what happens. Okay, so now you'll notice that gave us a red here on this particular character. So let's try the middle one, which I believe is green. I'll use the same offset. It'll be a different line because we scroll. Zero. And so now 2 will give us the second bit. And that's green, as I thought. And the last one should give blue. And indeed, that is blue, so it might be difficult to see. Now, if we want bright, just make it easier for you. That means we just need to add to any of these an 8, in fact. So we just need 8 plus 4, 2, and 1. So that we can remember from that. Now let's see 8-1. Now to make these bright, I don't know if I'm going to end up in the middle. Well, let's see where we go. C, A, and 9. There's a bright red. A, light green. Oops. And 09, bright blue. Now, of course, we can mix them up. We could have, if you have red, it's red, green, blue. It goes bright, red, green, blue, like that. Okay. Now, I just happen to know because I'm used to this. That red and green gives you yellow. Mix red and green together, you get yellow. So what is that now? If we wanted a non-bright yellow, we need 4 and 2. So we need 6. Yellow. Yeah, I should type it into a file. Brightness, red, green, blue. So if we want dim, red, and I'm not talking about the background, so foreground, red equals 0, 4, green is 2, and blue is 1. Okay. Okay, and if we want bright, we need to add 8 to all these. So 8 was C, 4 and 8, 8, 9, A, B, C, and then 8, 9, A, and 9. All foreground. And now for the mixtures, red and green is yellow. So that's 6. So for bright yellow, we got to add 8 to 6. 8, 9, A, B, C, D, E. And red and blue is magenta. That's red and blue, which is 5. bright magenta would be add 8 to 5, 8, 9, A, B, C, D, and green and blue is cyan. Green and blue, which is 3. So bright cyan is 3, 8, 9, A, B. Okay, now I'm getting another box. Mix them up quick. Good enough. Now what do we need? What is it? C8. $21. C80. And we want one more. So let's see about dim yellow. So that should be 6. And there you go. And bright yellow, E. There you go. This time it didn't scroll, so it went on top of the other one. And similarly, we can go on to the next character. And we can do backgrounds in exactly the same way. I can switch that E. Let's make the background red. Bright red. Bright red is 4. That would be C for bright red, and E for the yellow. So there you go. Now, why am I showing you this? Mostly for fun, but this can also be useful. For instance, I made a little batch program, a couple of batch programs, as I always do. And one of them does this print screen. These go by pages, okay? Each page is 25 lines. And my batch program takes in, well, let me show you that. I'll show it to you. Now it's actually more work here than required, but essentially what it ends up doing is copy from B800 over to A800, which isn't being used. That's for graphical memory. And the first argument is the number of pages, and I can only see 2. So if I just do full screen 2, okay, now this has been copied into the A segment. Now to retrieve it, I have another batch file called RS to retrieve. And again, number of pages, the base page, which again, I'll let that be 0, because that's where I copied to. And then I can set a destination page. I might want to retrieve, let's say, only half of it, and maybe put the top half and the bottom half. So for instance, if I cleared this out, one page, and base page 0, and I'd like to put that on the bottom. So there's the retrieval of the top page, because I've selected the top page 0, one page from the top, from the 0th offset, and I put it on page 2. I could also, if I want, put page 1 at page 2, and that's the other part. Or I could, for fun, I could take my fancy logo, print screen 2, and if I wanted, let's see now, how does it go? Number pages, base page, and I've forgotten now. Number pages and offset. Okay, so 0, and let's say 2. Now that means I should still have what I had in the A's, and I should be able to restore, let's say, one page from offset 2 to 0. No, it's not the one I want. Is that right? No. 2 to 0. Oh no, that makes sense. Yeah. So these were here's the ones that we had before with that colored thing, and these are the new ones. So for instance, I could take one from page 3 and put it at 0, and that's this. So here, with a batch file, I'm able to take multiple print screens of different pages and recall them if I might need them to play around with them, or just to fool someone. One thing you could do is put this restoring into a batch file and make a screensaver that alternately shows one picture and then another and another and so on. In fact, why don't I do that? Just a minute. There you go. It's my screensaver batch file. Batch file screensaver. You can't see what it's doing, but stop there. All it's doing is just calling that same restore screen 2 pages worth from either page 0 or page 2. I could mix it up if one wanted. Make this +1. Let's see what happens then. So it gets a bit of a scroll going. Yeah, in fact, it is a scroll. It's a rotating scroll. If I recorded another set of pages, I could have it scroll even more. Anyway, sorry for that little diversion. Now, where were we? Oh, I got that. Where are we at? This is where I want to be. Right. So, okay. So what we have now at this point are some basic utilities. We have an entry point with our RVs and our RCs. We have the beginnings of a standard calling convention and simple scripting in an assembler-like language. Now, what do we want? We want better scripting for function calls, we shouldn't have to do all that pushing and popping and restoring the stack. That could be handled in a script. Simple operations like plus and minus could easily be handled in a scripting manner. One thing we don't have and desperately need is memory management. Now, I've been allocating memory from the stack using our stack frames, and that's fine. Except memory allocated on the stack like that, obviously, disappears when the function goes out of scope. You remember, it's this. Now these two lines just wipe out our stack allocation. So the stack memory is only good as long as we're in the scope of our particular stack frame. So what we like is memory that lasts longer than our function scope, and that would be a static type memory, which is often called a heap, a global heap sometimes, or a static heap. Most assemblers, I'm not talking about C here, have something called a struct keyword, which allows you to define data in a structured manner. Like we might say struct, I don't know if it's caps or smalls, and you give it a name. And then underneath you give offsets, like or you might say word, value 1, and you might have another word, value 2, maybe a byte, and so on. And then later on in your code, you can define a particular variable type thing as being a type struct. So if you had that, you had a variable which doesn't matter where it came from, the stack or heap or a register or whatever. You can then reference an offset from this particular address in memory. So this is basically a pointer. This could be a pointer. You say var myvar dot val1, and the assembler will dutifully take you to the 0th offset from this variable. Similarly, 2 will take you to the next word offset, and so on. Now this is available in C, and it follows exactly the convention in most assemblers. And of course, we want a tighter and more natural binding of code with its related data. Now, we could take what we have and build all this stuff, build on top of what we have and get there, but there's limited time, so I'd like to jump ahead to C, using C, and I gave links in one of the previous videos as to where you could find one of the free Microsoft compilers for compiling C programs in Win32. I would suggest using Microsoft compiler because that's sort of an industry standard. You can use any compiler you want, obviously, but it's probably best to be familiar with what you're likely to run into in an actual working environment. And then we'll move on to C++ and see how all this relates to C++. Now I'm going to put those links, those same links, in the video description. So links in description for the particular version of Visual C that corresponds with the one I'm using. You could use a later version. Mine is the version 8, it's Visual Studio 2005, which is not 100% compatible with Windows 7, so you might want to use a later version. It should all work out the same for anything we're doing. Simple programs in C and then C++. Okay, so next time we're going to change formats once again, and we'll be looking at C, which should be an easy step for you. But I'd like to see how C and what we know so far are related. Okay, see you then. Bye.